Chapter 3, forced vibrations. Up until this point, we've just been talking about systems where we pull the spring back and we let it go, and the system has a free vibration. We haven't been adding force to it, right? And we've been showing that by mx double dot plus cx dot plus kx equals 0. And the 0 means that we have no forcing function. So this entire chapter is about replacing that 0 with a forcing function, right? So first what we want to do is define our free body diagram. And again, we have systems that typically look like this. We have some sort of spring. I'm going to drop the damper for a while. We have a mass. Spring K, still positive x to the right, still frictionless bearings that I roll on, and now I'm also going to have a force applied as a function of time to the right. So if I draw out just my free body diagram of that system configuration, I get a mass. I have mass and gravity acting down. I have a normal force acting up. It doesn't matter. Those will cancel. If I'm moving a little bit to the right, I have a force acting back, which is F of K, and I still have a force acting to the right, which is capital F as a function of time. So we need to develop a solution for the equation of motion for our ordinary differential equation here. And so we're going to start by just making some assumptions, tossing them into the equation and seeing what lands, right? So first, I want a sinusoidal loading, right? If I just pull to the right, I don't get any vibrations. It's a vibrations class. So I'm just going to say, you know what? F of t, that was fun and all, but let's make that a little bit more defined. I've got F naught, which is an amplitude, cosine of omega t. This is just going to give me a forcing function that looks something like that. I'll make it another color. We'll make it blue. Okay, so now I can write out my equation of motion with this new forcing function knowledge. And that's going to be mx double dot. I'm going to go with a function of t plus kx as a function of t equals capital F naught cosine of omega t. A lot of times we drop the t on the left-hand side. I added them back here because cosine's got a function of t. But we can definitely drop it again. If I want to get this into a standard form, I need to divide by what leaves my acceleration term. So I'm going to be left with x double dot. I'm going to drop the t plus omega n squared of x equals, now I've got a lowercase f naught cosine of omega t, right? So the lowercase f naught is different than my capital F naught, but this can simply be written as, lowercase f naught is equal to capital F naught over m, my mass normalized amplitude of my forcing function. I now hit a problem. My equation of motion is a second order linear non-homogeneous differential equation. It's non-homogeneous because there are no terms on the right-hand side of the equation. So one way to solve an ODE of that form is to take the sum of the homogeneous and particular solution. So if you think back to your ODE class, you might have talked about homogeneous and particular solutions. This is, from an applied mathematics sense, x is equal to x of h plus x of p. And again, x here is what we're trying to solve for. So another way you could write this is x at a given time t is equal to x of h plus x of p at your given times. Again, the t there is just implied. So knowing that the solution is a sum of two parts, and we have oscillations caused by the spring mass, and we have oscillations caused by the forcing functions, you might be tempted to just split those up. But these two forces interact with each other, right? So if we think back to our previous solution, right? Let's just write a solution for our homogeneous function, and that's x of h is equal to a sine of omega n t plus phi. So it's the exact same expression we had before. We're just redefining it as x of h. And so we're going to say that the oscillations caused by the spring mass in this case will be the particular solution. Sorry, will be the homogeneous solution. And the oscillations caused by the forcing function are the particular solution. This is a very common way to do it, but it is generally just an arbitrary choice that we made on our side to make the solution of the ordinary differential equation work out. Okay, so that means that I can do x of p is the right-hand side of that equation now. And I'm going to have x, which is a new term, capital X, a new term that we're defining, cosine of omega t. Right? Because I have x of x equals my homogeneous plus my particular solution, I now get a solution that x is equal to my homogeneous, which is a sine of omega n t plus phi plus x cosine of omega t. This is one of those equations that if you don't write much down, at least write this one down. That is going to be our solution for the forced function. It's omega n. So again, if it wasn't clearly defined, I apologize. This x cosine of omega t is this omega here, which is our frequency of the forcing function. So when you look at this expression, this omega n here, this is our frequency of our system. And this is the frequency that we force our system at. And there's lots of interesting things in the world of vibrations that happen when the frequency that you force the system at aligns with the frequency that the system naturally wants to vibrate at. That's really one of the core concepts of vibrations, which is resonance, and we'll get to that in a future subsection. Okay, I've got x of t, a sine omega n t plus phi plus x cosine of omega t. We're very good at solving these solutions. We know what we have to do. We've got to take the derivative, get velocity, take the derivative again, get acceleration, apply our boundary terms, right? Not too difficult. I'm going to skip over some of the details there. I'm just going to write the answers because we've done it about 5 times at this point. So I've got and then also I don't care about my velocity because I don't have damping, right? So I'm gonna pull that out. So I've got x of p is equal to x cosine of omega t. Let me go back to pink on that, or magenta. And then x double dot of p is equal to negative omega squared x cosine of omega t. So if I substitute this back into my standard form of the equation that I have before, I'm going to get negative omega squared x cosine of omega t plus omega n squared. This one's n, the first one's just omega, x cosine of omega t is equal to F naught, which is my mass normalized amplitude of my forcing, cosine of omega t. Right? So as long as, if I want to solve for x in this term, as long as cosine of omega t is not equal to 0, right? As long as it's not equal to 0, I can move some terms around to get x, capital X, is equal to F naught over omega n squared minus omega. And this is one of the things that if you don't write much down, write this down. That's the solution for the capital X above. All you need to know is the mass normalized amplitude of your forcing function, the natural frequency that your system the frequency that your system naturally wants to oscillate at, omega n, and the frequency that you're forcing it at, omega. You can see that if omega n equals omega, you have F naught divided by 0, which becomes undefined, right? Which might cause an issue later. Something to see from this. We don't have to spend too much time on it. So as long as omega n is not omega, right? So as long as those two are not equal, we can get x of your particular solution is equal to F naught over omega n squared minus omega cosine of omega t. And we can expand this back out to a total solution by just throwing back in our homogeneous solution, which we've been working with, right? So I can just have x of t is equal to a sine of omega n t plus phi plus F naught over omega n squared minus omega cosine of omega t. And you can write this one down. It's pretty important. I'll circle it in red, but it's probably not the most important equation because it's what we had before, but we have just filled out all of our parameters. Yes. There's a squared there, correct. And there should be a squared here also. And there should be a squared here also. I apologize. Yep. Again, this is not a solution if omega n equals omega. That's when our system is in resonance. Now that we have a solution for this, we can set in our boundary conditions and solve for some parameters, right? So let's go ahead and do that. So let's force our initial conditions for the coefficients of A1 and A2. So I can say x of 0, which often we'll write as x subscript 0, is equal to a2 plus f naught over omega n squared minus omega squared. I can rearrange this a little bit to get a2 is equal to x naught minus f naught over omega n squared minus omega squared. So again, we can solve for the terms in velocity now to apply our initial condition for velocity. And let's go ahead and write that out. It's not super important, but x dot of t, is going to put an of t there, is equal to, for all of our velocity terms, is going to be a1 omega n cosine of omega n t minus a2 omega n sine of omega n t minus our x parameter, which we've added to the solution from, which we're adding to the solution in this chapter, which is going to be omega, that comes from the sine of omega n t, f naught over omega n squared minus omega. Again, the second omega is what we're forcing it at. And then we have sine of omega t. All right, so when I've got velocity equal to 0, so I've got at t equals to 0, almost all of this drops off. And so this simplifies to x dot of 0, which is also equal to v0, which is just equal to a1 omega n. And then real quick, a1 is equal to v naught over omega n. And if you don't write much down, write that a1 down and that a2 down.
Should the omega in the x dot formula be straight?
No. Yeah. Thank you. Okay, so if we combine all of these equations and all of these initial conditions, we get an equation that takes up the left to right side of the paper, right? But let's go ahead and write it down. This is an equation for the displacement of the mass at any given point in time, knowing your x naught and your v naught for a forced function, right? It's just combining all the terms that we've previously written. But if you want to write down the full solution, it's x of t is equal to v naught over omega n. It's your initial velocity over the natural frequency of the system, multiplied by the sine of omega n t, plus, I'm going to do big parenthesis, x naught, x subscript 0, that's your initial displacement minus f naught over omega n squared minus omega cosine, I'm going to make that parenthesis a little bit bigger, of omega n t plus f naught over omega n squared minus omega cosine of omega t. That is a perfectly fine solution. I'm not a huge fan of it. It's long. It's perfectly explicit, right? But it's a little long and a little bit hard to comprehend. So, and there's a square there. And there. So, not a huge fan of it. It's just kind of hard to digest. So, let's write this just like we've been writing our other one, which I think is a much better way to write it. But the solution is exactly the same. X of t is equal to capital A sine of omega nt plus phi. And that's an A with no subscript, because it's just the amplitude of the system, plus capital X cosine of omega t. Now I need a value for my A. If we go back and look at the triangle, Pascal's triangle, we can build out a value for that A. And that becomes capital A is equal to very large radical V naught over omega n squared plus x naught minus capital X. That whole term is squared. So now I need to know my phi, which is my phase angle. Again, this is coming from the triangle. We're not writing out the triangle, but you can go back and look at how you would get that from the triangle. And that's phi is equal to the tangent, inverse tangent, big parenthesis of omega. Sorry, there's going to be a division here. So omega n multiplied by x naught minus capital X, close the parenthesis, close the big parenthesis, all divided by V naught. And I still need to know my capital X, right? So capital X is what we had before, F naught over omega n squared minus omega squared. And that is a solution a full solution to a forced 1 degree of freedom system problem without damping